I thought it might be a good idea just to take a look at how to make a forecast. In other words, if we take a look at your syllabus, and we'll go here to your Scholar site, and we'll click on the syllabus, you will notice that one of your homeworks, actually homework number 2, is to make your first weather forecast. So let me just walk you through a few items. Also, I'm going to, with this particular video, you'll notice that the following week, one of the assignments that you have to submit is lab number 4. It talks about forecasting for surface features, fronts, clouds, winds, moisture, and precipitation. So I think it might also be a good idea to look at what we call a surface map. So the first thing I'm going to do to make a forecast, I'm going to click on the forecasting link, which you will go to Ocean and Atmosphere. You should have set up an account on here. That was one of the assignments from the first week. And let me go ahead and log in as a student. I've actually forgotten my student name, so let's try. Actually, I think this might be it. That is correct. So one of the things that you'll need to do, and this is the only time we use ClassNet, is to make a forecast. The only assignment there is the 00 forecast. I will go ahead and click on Complete. And lo and behold, you see some of the things that we're forecasting for. I just want to talk about this page a moment. There's a ton of information available for you with all types of links. For what we will be forecasting for in this class, we'll be forecasting for Des Moines. The identifier for that is KDSM. And we will be forecasting for morning temperature 12Z, which after doing one of the first assignments, you should know that that is actually for 7 a.m. Now keep in mind, as you're sitting down to do a forecast, you are forecasting the weather for the next day, which means you need to submit this forecast before 11:59 p.m. because once the clock moves over to midnight, then we've moved to a new day. So as I'm looking at this 12Z temperature, I'm forecasting for what I believe will be the 7 a.m. temperature for the next day. And notice here we've got this link that talks about basic temperature forecasting. If you click on that, there is a series of a few PowerPoint slides, 12, and it talks about the different types of forecasting temperatures. One example of forecasting temperatures is called persistence. In other words, you find out what the 7 a.m. temperature was today and say it will be the same temperature tomorrow. Sometimes that works. But you know, living up here in Iowa, you know that weather can change very quickly. And in fact, we have what we call cold fronts and warm fronts. We'll learn what those are in just a little bit in this course. But they move through and can change the temperature quite dramatically. So persistence doesn't always work. Another type of forecasting, observational forecasting. So you see, we know that typically weather patterns come from our west or southwest or northwest. So we just take a look out there, see what the temperatures are, and assume that it will travel to Des Moines within a 24-hour period. But I would encourage you, you can go down here and click this, and go through these 12 PowerPoint slides along with the video on forecasting for temperatures that I've provided on Scholar, and this will get you off to a good start. So what you would do is that you would enter a temperature, and the purpose of this first forecast is for you to get used to actually submitting a forecast assignment. So I'll just put a, let's see, I'll just put a temperature in there. And I haven't looked at any maps yet. Cloud cover. Question number 3. Cloud cover to inhibit radiational cooling tonight. Well, that's a term that we're going to learn about in Chapter 2. But at this point, you really don't know what that term means. Well, you might want to go over here and take a look at this link. How do clouds affect cooling at night? And you see right here it talks about clouds restrict cooling at night because they absorb long-wave radiation emitted by the surface and lower atmosphere and re-emit a significant portion back. Wow, there's a term there you probably are not familiar with at this point. Long-wave radiation. Well, that's Chapter 2. So the idea is that as we go through Chapter 2 and we talk about the exchange of energy between the Earth's surface, the sun, the atmosphere, that has an impact on temperature. So this particular program, what it looks for, it looks to see if there are 3 or more, well actually this has to do with cloud cover. I'll come back to that in just a moment. But here's an example of how clouds can inhibit cooling. If I click on this, see the clouds here. And what these arrows represent, and you'll learn about this shortly as we go through Chapter 2, is long-wave radiation being emitted by the Earth's surface. This long-wave radiation that emits energy, the cloud absorbs it. We'll learn in Chapter 2 that when any body absorbs energy, the molecular motion begins to increase. And the way that we define temperature is the average speed of molecular motion. If the molecular motion begins to increase, temperatures will increase. If the molecular motion decreases, then temperatures will decrease. Here's a simple example of this that we used to do in grade school. If you take the palm of your hand and rub it against a desk, and the faster you rub the palm of your hand on that desk, you'll notice that you'll begin to feel heat in the palm of your hand. Well, the average molecular motion, the molecules in your hand, are moving faster and faster as you move it over a desk or over a table, which would mean an increase in temperature. But I'm jumping ahead a little bit here. You know that during a clear night with no clouds, typically it's colder. In fact, some of our coldest weather in January and February, when we have clear skies, some of our coldest temperatures occur at night. And we'll learn in Chapter 2 it's because the radiation that is given off, long-wave radiation, given off by the Earth's surface, continues unabated off into space. And so any object that loses energy or emits energy, and again this is in Chapter 2, will begin to cool. So you see back here with these clouds, the clouds absorb that energy from the Earth's surface, and as we'll learn from an equation called the Stefan-Boltzmann equation, E is equal to sigma t to the fourth, and that just simply tells us that the amount of energy that a body emits is proportional to the fourth power of its temperature. So what we're saying, something with a higher temperature will emit more energy, and that energy will be emitted back to the Earth's surface, and since the Earth's surface is absorbing that energy, it's going to be warmer than what it normally would be. So now you know why with clouds at night we typically don't drop as much as we would on a clear night. So forecasting the weather, forecasting for temperatures, you probably should understand a little bit about energy and the exchange of energy. And that's why we're going to cover Chapter 2, is we're going to look at the exchange of energy. It's a critical chapter. Question number 4. Well, so I'm going to put, as I look outside, I don't see very many clouds, and it was pretty clear today, so I'm just going to assume that we will not have any cloud cover this evening. Now again, I'm not looking at any maps because I'm sitting down just like you would and assuming that you do not have any background in forecasting, and so the first forecast that you make you're going to be doing it based on observation. Now, you'll learn as we go through the course what to look at to see if there's going to be cloud cover coming in. And in fact, you'll notice I have a video here that you can view on forecasting for clouds. Here it is. Page. And you will see that we forecast for something called a front. Now, if you click on this link, you will see how the forecasting program, because this forecast that you make is being graded by a computer program. And so you need to understand what the program is looking for. So basically, here's an idea of an example of a front near Iowa. If you have any front that passes within basically the region of Iowa, actually goes down a little bit into Missouri, but if you have a front that passes through Iowa, whether it's a cold front, warm front, or if you have a stationary front sitting across the state of Iowa, that's what the computer program looks for. Specifically, it looks at let me back up here a second. So it talks about a fast-moving front. Let's assume it moves about 90 miles in a 3-hour period. Then what would happen is the program checks for the appearance of a front at specific times, 5 hours before 12Z and 18Z, 2 hours before 12Z and 18Z, and 1 hour after the forecast time, basically in the state of Iowa. So if there is a front, now you're forecasting for the location of a front at 12Z and at 18Z. So if you think a front is going to pass within the state of Iowa at 7Z, which is 5 hours before 12Z, 10Z, which is 2 hours before 12Z, and 1 hour after 12Z would be 13Z, then the program says a front has passed through. Now, if you take a look at this, here's an example of a warm front and cold front. Cold front is represented by this blue line. Notice these triangles. These triangles point in the direction that a front would move. So this front is typically moving to the east. We have what we call a warm front, and notice it has a semicircle there, which indicates that this front is moving off to the northeast. And then we have something called a low pressure center. Now, you'll recall that here I've put out a link to a nice tutorial on fronts. So if you go to this link, this is a link over at the University of Illinois that talks about the different types of fronts. So for example, if you click on the cold front, it talks about what a cold front is. It shows that a front here, this blue line, is moving off to the east-southeast, out ahead of a cold front. Typically you would have warmer temperatures. Behind a cold front you would have colder temperatures. So as this front moves left to right across this screen, it will be replaced by cooler temperatures. Here's an example of a cold front that is just entering northwest Iowa. Notice that reporting station, it's probably Sioux City, is reporting 55 degrees. But if you go a few hundred miles across the front, back behind the cold front, it's 38. So as a cold front moves through your area, temperatures will decrease. And it talks about some of the characteristics with a cold front: the winds, the temperature, pressure, clouds. You should take some time to review this. This will help you when trying to forecast for fronts. So you're beginning to see that there's quite a bit of information available up on Scholar to help you with forecasting. Now let me go back to this. And so you have to forecast for a front. I haven't looked at anything, but for example, if you think a cold front is going to move through, per what we looked at here, the different hours that the program looks for, 5 hours before 12Z, 2 hours before, and 1 hour after. If you thought a cold front would move through, you would click on it. And then we forecast for something called advection. You have no idea what advection is at this point. We haven't gotten to it. But if you click on this link here, it provides you with examples of what advection is. And you see the definition given here. Advection of temperature is the horizontal transport of temperature by the wind. In other words, think about this. Now, we're not talking about vertical direction, but we're talking about horizontal direction. Some of our warmest summer days, and I'm talking about 100-degree days, is when the wind is coming from Mexico, Texas, and Oklahoma and moving into Iowa. That wind is not moving, we're not talking about the wind moving from the surface up, but we're talking about it moving horizontally, coming in from Texas, Mexico, Oklahoma, Kansas. That wind is transporting warmer temperatures. So when we talk about temperature advection, we're talking about the movement of air. And now air has characteristics. It has characteristics of a temperature, of moisture, because air can carry moisture. We'll talk about that in Chapter 4. But if you click on this link here called Advection Help, it takes you to some PowerPoint. It gives you an idea on how to do advection. Now you'll see some of these PowerPoint slides here in the transfer. It's a little garbaged up, probably would be the best way to do this, to look at it. But here's an example of cold air advection. If you completed homework number 1, I believe it's homework number 1 on the station model, you will realize that this is a 20-knot wind from the north, and these lines here are lines of equal temperatures, which we call isotherms. The air is getting colder as we go further to the north, but the wind's coming from the north, bringing in colder air. And so if we have at least a 10-degree difference across the state of Iowa, which is roughly about 280 miles, I would assume, north to south, roughly 300 we can say, and a 10-degree temperature change here in this example, that's some significant cold air moving in from the north. Here's a general example of advection, north wind, temperatures decreasing. To give you just, I'll give you something to look at here. If you see a 10-degree temperature difference of about 300 miles, and you have at least a 10-knot wind, then you're going to have a significant change in temperature due to advection. As we'll learn in Chapter 2, and you know this intuitively, we don't necessarily have to have the winds blowing to have warm temperatures. If we have clear skies and the sun is at a high angle, sitting high in the sky, the energy, as you'll learn from Chapter 2, the shortwave radiation coming in from the sun, when it reaches the ground, when it reaches us, begins to excite the molecular motion of the ground, your skin, temperatures begin to increase. So that's one way you can increase temperature, an energy source. Another way that you can impact temperature is to move it from one region of the U.S. to another. And typically at this time of year, we'll see a lot of warm air advection. So if you're outside and you have a 10-knot wind and temperatures are changing by about 10 degrees over a 300-mile direction, then you're going to have significant advection. So let's see, I was outside earlier today. The winds were coming in. They were pretty warm. Wind gusts were right about 15, 20 miles an hour. Sustained winds was about 10. So I'm going to say we'll have significant warm air advection. It would be nice if I looked at some maps to confirm this, but we're not quite there yet. 18Z temperature. So now you've got to forecast for 18Z, which at this time of year, which would be summer, you're looking at 5 hours from 18Z would be 1 p.m. So you're forecasting for whether cloudiness will hold down daytime temperatures or not. Today was clear. If I assume persistence forecasting, I'll say that we will not have significant cloud cover to hold temperatures down. So I'll say it won't affect. If you click on daytime cloudiness and temperature, it talks about how the computer program that scores your forecasting, what it looks for. It looks at 15Z, 16Z, 17Z, and 18Z. So it looks at those 4 hours, and if 2 or more of these times report at least 75% cloud cover, then the computer program will score it as significant cloud cover, which would keep temperatures down. So that's what it looks for. So you really need to go back and take a look at these links to see what the computer program, how it's scoring, or how it will score or verify each of these questions. And then we have to figure out if a front is going to pass through 18Z. Recall that from the 12Z help link, it will check for the presence of a front 5 hours before your forecast time, which is 18Z, which would be 13Z. 2 hours, well, let's see, I've already forgotten. Let's go back up here. So it will check for the appearance of a front 5 hours before, which would be, since we're forecasting for 18Z front, would be 13Z, 16Z, and then 19Z. If there's a front within the confines of Iowa at any of these times, then the program will verify as a front present. So let's just say I say no fronts within 140 miles any direction of Des Moines. I also have to predict for advection. I'll just go ahead and put something in here. At this point, I just want you to get used to entering values. Now I have to predict the wind speed at 18Z, which is 1 p.m. the next day. Winds this afternoon, like I said, we're gusting around 15 to 20. If I assume by persistence that the same winds will persist into tomorrow, then I'll say 10 knots. And let's see, the wind direction, when I was out there, it felt like it was from the southwest. No precipitation today, so I'll assume none here. And question 13. Now question 13 has to do with analyzing why or why not precipitation will occur. Regardless of what you put in question 12 here, you will always have to analyze or answer question 13. Now here's your first major breakthrough in this course. When we're looking for the presence of clouds or precipitation, we need two things. One, we need sufficient moisture, and that probably makes sense to you. If you're going to produce a cloud or if you're going to produce rain, you probably should have sufficient moisture in the atmosphere. However, the other item is we need to be able to lift air vertically from the surface. Now, we're not talking about advection. Advection is the horizontal movement of wind. What we're talking about here is convection, or the vertical movement of air. So, when I was out there today, it felt really dry. I mean, any perspiration that I had was drying pretty quickly, which tells me there's not a lot of moisture in the air. Unstable atmosphere, well, what is that? Well, if you click on this link here, how do these factors influence precipitation? It talks about what an unstable air is. And the gist of it is that if you have a temperature difference between 850 millibars and 500 millibars, well, first of all, you're probably asking yourself, what is an 850 millibar or a 500 millibar? I'll talk about that in just a moment. It's different layers in the atmosphere. if between these two different layers in the atmosphere you have at least a 25 degrees Celsius difference, in other words, if the 500 millibar surface is 25 degrees cooler than the 850 millibar surface, then you have an unstable atmosphere. Well, big whoop. What does an unstable atmosphere mean? That's Chapter 5. We'll get to that soon enough. So let's say I said it was dry, so I want to uncheck this. I don't want to check moisture if it's dry. I can leave it blank, or I can say, yeah, tomorrow will be unstable. Now, I said no on precipitation. But one of the reasons why I said no is if I think there's not enough moisture, and you'll learn how to tell if there's sufficient moisture very quickly in this course, then I'm probably not going to get any precipitation. Fronts and an unstable atmosphere help to lift the air. Remember, there are two items that you need to produce precipitation and clouds. You need sufficient moisture, and you need a way to lift that moist air upward into the atmosphere. Now, once you have completed filling all of this in, this is very important, because all the hard work you're going to go to will be for naught unless you press this submit button. Press the submit button, and then you can go back and check to see. Let's say you were watching the evening weather. Let's say you submitted your forecast about 2 o'clock in the afternoon. You went home and you saw the 10 o'clock weather, 10 p.m. weather, and they said, hey, it's going to rain. Well, you're going to want to go back into this forecast, and notice it saved everything as long as you go back and do it the same day. Once we switch over past 11:59 p.m., then this all goes blank again. Notice I left off an 18Z temperature, so I need to make sure I put that. Today it felt like it was about 80, so I'll put 80, assuming the same thing will occur tomorrow. But old Brad Edwards, let's say he says, oh, it's going to rain tomorrow. Now, you could go in. Right now, since you don't know much about weather forecasting, you might have to take his word for it. I know Brad. He's okay with me using his name. So I can click on yes, that there will be precipitation, and apparently if there's precipitation, there might be sufficient moisture. So as long as I submit this again before 11:59 p.m., then it will take my latest submission. And then if you're not sure if you submitted it, you can always go back, click on it, submit it again. Click on submit. Now, what I did is I went back and I actually made a forecast a few days back. So if I go over here to answers, wait, that's not the one. Oh, here we go. You'll see that I actually submitted a forecast back on May 13th. Now, I sat down on May 13th and I was forecasting the weather for May 14th. So now you're not going to get immediate grading on this forecasting assignment, because what happens, well, first of all, the next day has to occur, and then after that, then that data has to be uploaded to the computer program, then the computer program grades it. So rule of thumb, the day you submit a forecast, you're submitting for the next day's weather, but you can expect to get this graded by the computer program 3 days after you submit it. So May 13th is when I submitted it. Today's May 17th, so May 16th it should have been graded. So if I click on answers and I scroll down here to the bottom, I can see I got a 32 out of 36. It's not bad. Right now, at the beginning of this course, in the first couple of weeks of the first 2 weeks of the course, if you score at least a 20 out of 36, I will consider that a very good forecast, because we're spending the first couple of weeks learning how to forecast the weather, learning which maps to look at. So there's still a lot we have to learn. So if you've got a 20 out of 36 at the beginning of the term, that's not bad. Keep in mind, if you go back to the syllabus here, you go back to the syllabus here, you're going to make at least 30 forecasts during the semester. And I'm going to take your 25 best forecast scores. So if you're going to do 30, if you do all the homework assignments, then I throw out your 5 lowest scores. Well, let's say you get ambitious and you decide to do 50 forecasts. And to do that, you'd be doing one every other day, basically. Then if you do 50 forecasts, I'll take your best 25 forecasts from those 50. In other words, I'll throw out the lowest 25 forecast. Like I mentioned before, those students that do 30 to 35 forecasts in a semester tend to do very well with the forecasting part of their grade. So it behooves you to do as many forecasts as possible. Now you can only do one a day. You can go back and change it, but you can only do one forecast a day. So I got a 32 out of 36. Let's look at all the questions. The thing about this, there are 12 questions to this, and they're worth 3 points apiece. And even if you get the question incorrect, you're still going to get a point. So even if you miss all 12 questions, you're still going to earn a 12 out of 36. So let's take a look at this. So back on the 13th of May, you see up here, when I sat down to make a forecast for the 14th of May, I predicted a 12Z temperature. Now keep in mind that's 7 a.m. It's a 7 a.m. temperature. I predicted 45. Notice the points I got out of this. 1 out of 3. In other words, I missed it. Now, what's nice about this is you do not have to nail the temperature dead on. You've got a plus or minus span. In other words, the program said that if I would have put anywhere from 49 to 59 in here, I would have been marked as correct. So if there's a plus or minus 5 on the temperature, what is the actual temperature? Or what was the actual temperature for 12Z the day after I made this forecast? If 49 to 59 is the range, it would be halfway in between. So the actual temperature for the 14th of May, which was the next day, was 54. So 54 was the actual temperature, so minus 5 would be 49, and plus 5 from 54 would be 59. So you get a plus or minus 5, so you don't have to nail it dead on. Cloud cover, well, it either is or it is not. I said would not be significant to inhibit radiational cooling, and sure enough, you'll notice I got 3 out of 3. Notice it said answer was 2. In other words, it was choice number 2. This is choice number 1. This is choice number 2. For question number 4, I said, well, there won't be any fronts passing through Iowa. And lo and behold, I got 3 out of 3 because the answer was choice number 5, which would be no front. Advection. I said advection would not be significant. The answer was choice number 3. Lo and behold, that's choice number 3. I got 3 out of 3. So then I had to forecast for an 18Z temperature. It says 3 out of 3 on the points, so I got the temperature correct. I put 80, but that was not the temperature. Can you tell me what the exact temperature was? Well, if it's a plus or minus 5 range, 73 to 83, halfway between 73 and 83 is 78. So the actual temperature at 18Z was 78. I was within the plus or minus 5 from 73 to 83. Temperature influence. I said there won't be any clouds. The answer was the second choice, so I got that correct, 3 out of 3. Same thing for front. I said there would be no front at the 18Z time. That was correct. Got 3 out of 3 on that. For advection at 18Z, I said there won't be significant advection. Well, that's correct. The answer was choice number 3. I got 3 out of 3 there. Now, wind speed at 18Z. Now, I purposely missed this. And the reason that I did, I wanted to make sure that the forecasting program was working correctly. By the way, I've been doing this for 15 years. We've never had an error in the data. Now, we've had occasionally, once a semester, no data has been reported, but I've never had incorrect data at this point. So I put 30 knots. It's rare that you're going to get sustained 30-knot winds. Well, like temperature, you have a plus or minus 5 for winds. So if you put anything from 6 to 16, the actual wind speed was 11, because 11 is halfway between 6 and 16. So I missed that, got 1 of 3. Notice here, wind direction, I put southwest. The answer, interesting, it gives me south, southwest, or west. The middle one is the correct answer. The actual temperature was southwest. But if I would have put south or west, it would have still been marked as correct. I got 3 out of 3 there. Now let's take a look at this, what determines wind direction. Here are the different wind directions. And I want to show you this compass rose. So notice the actual answer was southwest was the correct answer, but the program said west or south would be correct as well. I'll go back here just to show you again. So the actual wind was southwest. South or west would have been marked as correct too. And if I go back to that compass rose, so actual wind was southwest, south or west. So you've got 8 directions here. So we got north, northeast, east, southeast, south, southwest, west, northwest. Again, keep in mind, wind direction is the direction the wind is blowing from. You'll learn that in one of the first assignments with station model. You don't have to be exact on the wind. So you can be plus or minus 1 octal, since we're talking about 8 directions here, plus or minus 1 octal. So if the actual wind direction was southwest, 1 octal over is south, and another octal over from southwest is west. If the actual wind would have been east, then if you'd have put northeast or southeast, you would have been marked as correct. So you don't have to be exact with it. It gives you a little bit of leeway there. Let's see. I said there was going to be no precipitation. The answer was the second choice. No. Got 3 out of 3 there. Precipitation influences. I said there would not be sufficient moisture, no front, but I said an unstable atmosphere. In other words, I predicted that there would be a 25-degree difference if you click on this. And for the unstable atmosphere, it says if you have at least a 25-degree difference between 850 and 500 millibars, then it is considered unstable. Now keep in mind, this is a link here you can click on, and it talks about how to calculate stability. So you can go through these different links here, or these different PowerPoints, and it will show you how to do that. I'll show you an easier way as we get through the class. So you can go through and you can check to see what you've been missing. If you find yourself consistently missing the same one, feel free to give me a call or drop me an email, and maybe I can help you out with a particular forecasting parameter that you might be having some issues with. Okay, so that, you can also click on scores to see what your scores are. Now you'll notice right here, here was the one I made on the 13th. Notice back on April 3rd, 2012, it says seen on Tuesday, April 3rd, 7:07 p.m., but not submitted. So when I looked at this, I did not hit the submit button, so it can't grade it. That's why it's important to submit. If you're not sure, go back and hit the submit button again. And then here's the one that I submitted just a few minutes ago. 5:36 p.m. It says submitted but not yet graded. So this one will be graded by the 20th of May. So I hope that helps you out a little bit, because according to the syllabus, I'll go back to the syllabus. Homework number 2 is to make your first weather forecast. And don't fret. I know you don't know how to forecast yet. That's why you're taking the course. And so as we go through the labs and we go through the video modules, you're going to be able to build your forecasting tool belt. Hang in there. You'll do fine.